Welcome to our 45th session. In today's session, we have finished up the MOS field effect transistor, and we're going to be focusing in on some novel devices. We're going to return to the metal semiconductor field effect transistor without the oxide, and we've already looked at that a little bit in chapter 20. We're going to be looking at the IV characteristics of that device probably in the next session. In today's session, we're going to be comparing the MOSFET to the MESFET, and then we'll be looking at some general rules for drawing energy band diagrams, specifically when we have two different materials. And we're going to be using those general rules to looking at a relatively interesting device called the High Electron Mobility Transistor, or HEMT. But before we get started, I'd like to share with you a clip from Rossini's La Cenerentola. This is the final aria from Act 1. We'll see the two wicked stepsisters and the wicked stepfather, not the wicked stepmother. We'll see the prince who's dressed as the servant is dressed as the prince, and of course Cinderella in her wonderful, beautiful gown. And let's enjoy, and we'll see you in about 3.5 minutes.
Signor Altezza in tavola, signor Altezza in tavola, che così, che bestia, quando si dice i simili.
Non sembra Cenerentola.
Pareva ancora a noi, ma riportata a voi, le nostre goffa terrante. Questa un po' più affettata, ma voi non la vedi da farci spaventare.
Quella sta nella cenere, a stracci solperabiti.
E qualche dubita, di qualche parte palpiti.
Ma non facciamo le statue, patisce l'individuo. Andiamo a tavola, andiamo a tavola, andiamo a tavola, andiamo a tavola. Poi balleremo il fece, e quindi la bellissima col me sarà sposare. Andiamo a tavola, si vuole giubilare, giubilare. Oggi che poco da aprire, per 4 vuoi mangiare. Oggi che fa da principe per 4 vuoi mangiare. Fatadini, Boschetti. I ruscelli sussurrando, gogheggiando gli augelletti. Sussurrando, fanno la limonata. Sussurrando, fanno la limonata. Occhi sotto terra, piano, poco, si sviluppa in certo fuoco.
Welcome back. Here are some of the topics we'll be covering in today's session. For the next two sessions, which will be the last two sessions, we'll be focusing in on three different kinds of field effect transistors. The MOSFET, which we've been covering, in session 36, so that's 9 sessions back. The MESFET, which we introduced in section 36, and we'll be looking at it in more detail. And then we're going to introduce a new kind of field effect transistor, which is the high electromobility transistor. And in the next session, we'll introduce one more type of field effect transistor at the end called the static induction transistor. So in this session, we'll be contrasting the MOSFET to the MESFET. In the next session, we'll be going over the MESFET IV characteristics in somewhat greater detail. And toward the end, we'll be looking at the HEMT and how to design a HEMT. And we'll end with the finale to the movie, The Soul Keeper. Okay, so let's get started. This is a hopefully familiar cross-section of the MOSFET. Let's see, I know it's a MOSFET because it has thermal oxide. It has three depletion regions. There's a depletion region underneath the oxide. If we have threshold or above threshold, there is an inversion layer, and then underneath the inversion layer, there is a depletion region. Beside that, there are two depletion regions due to the P-N+ junctions, one at the source and one at the drain. For very short channel lengths, L, the L is the distance from the channel from the source to the drain. As L gets very, very small, and as VDS gets large, this depletion region increases rather dramatically, and so we can get a situation where the two side depletion regions, one at the source and the gate, actually run into one another, and that's called Dibble, and that has rather disastrous consequences. And we mentioned before that one of the ways to reduce the depletion region, to push that red line further and further to the right, is to increase the doping, because the entire depletion region of a P-N+ junction is on the quote-unquote lower dope side. So the substrate side is the lower dope side. So the two ways we can decrease this distance here, which we really want to do, increase the doping or decrease the distance from here to here by making a shallower contact. And if we increase the doping, however, the threshold voltage goes up, which is not so great. It's more difficult to invert a highly doped substrate than it is to invert a lower doped substrate. So the best way to increase performance, to make the short channel effects as benign as possible, is to decrease the T-ox. Make this distance here this is the T-ox, as small as possible. And the problem there is we get to about 20 angstroms or less, which is 20 atomic layers or less. Then we start getting tunneling, because the electron is really a wave, and it can actually tunnel its way between the substrate and the gate, and any tunneling produces severe leakage, and that is a big problem. So the MESFET is a completely different device, even though we only changed the O to an E. This stands for metal. ME is a metal, and S is not necessarily silicon. In fact, it's not silicon. It is a generic semiconductor, so it's a metal semiconductor field effect transistor. The semiconductor that we generally choose will be gallium arsenide. So I don't know how that would work out in the acronym. You have to be MEG or something like that. But MESFET is metal semiconductor field effect transistor. And what we do here is we deposit a channel rather than create a channel. So the yellow is the depositive channel, and this channel exists over the entire wafer. We're just showing one tiny little tiny device here, but this yellow exists all over, generally a 6-inch gallium arsenide wafer. So here we have a channel, so that even if we have zero gate voltage, if we have a situation where we have no depletion region, we can have a conductive current. So that's one difference. And generally we'll have as I say, a gallium arsenide substrate, and it will be semi-insulating. And the reason we want semi-insulating, if we go back over here on silicon is generally going to be fairly highly doped substrate. So the substrate itself, if we didn't have a depletion region underneath the oxide, when we have an inversion layer, we would have huge amounts of current right through the silicon. That is not good. So in a MESFET, we have a semi-insulating or very high resistivity substrate, so that the entire current is confined to the channel. But other than that, we have the same VDS, have a source and a drain. And I've shown them into the substrate. Generally, that's not true. This is just to make figure 24.2 as close to figure 24.1 as possible. Okay. There are a number of other differences between the MESFET and the MOSFET. In the MOSFET, inversion is absolutely assured no matter what the gate material. Generally, the gate material is degenerately doped N plus silicon, N plus silicon, or if we get really clever, someday we'll figure out how to make a true metal gate. But no matter what the gate material is, if I put the right value of gate voltage, I can get this thing to invert. Here, however, we have a metal semiconductor. This is a semiconductor, even though it is a deposited channel, it is grown on top, or actually not really grown, deposited on top of the gallium arsenide substrate. So generally this will be also gallium arsenide. It's just doped generally about 10 to the 16th. So here we have a metal semiconductor interface or a Schottky interface, and if I don't choose the right material for the gate, I can have an ohmic contact here. So I have to make sure that I choose the right gate metal. Generally for gallium arsenide, gold is a good choice. So that is another of the differences. I'm not assured to having a Schottky barrier. I need a depletion region because I need to control the resistivity of the doped channel. And if I have an ohmic contact, I can't do that. So I must have a barrier here, and it must have a depletion region in the doped channel. Another difference between the MOSFET and the MESFET is cost. Cost for a high quality polished, ready to be worked 12-inch silicon wafer costs somewhere around $100. That's for 12-inch. I think now they have 15 inches, but somewhere $100 or maybe a little bit more would be a reasonable cost, while even a 6-inch gallium arsenide wafer with a deposited channel could be well over $1,000, could be $2,000 or $3,000, and only part of that cost is in the gallium arsenide. The gallium arsenide itself may be a couple $100. The cost is the deposition cost for the deposited channel. So now we're going to broaden our approach to energy band diagrams and to looking at different types of semiconductors, and we're going to bring two different kinds of semiconductors together, which may or may not, probably will not, have similar properties. So in order to do that, let's go back to the MOSFET, and this is a cut somewhere along the channel, and you'll notice what we have here, and this is something we've seen before. The first thing we note is that we have a voltage across the oxide and the silicon. I know that because I have band bending. If I have band bending, I have a corresponding voltage drop, and because the oxide and the silicon are both passive, then the voltage drops across the oxide and the silicon must be the same sense. So positive, negative, positive, negative. That's why the band bending is the same in the oxide as it is in the silicon. Where's the channel? Well, if we have strong inversion, the channel will be right at the surface. So we denote the fact that we have a channel right at the surface by saying, well, there must be electrons here. Now, there isn't much of a channel here because, well, actually there is. I take that back, because if we draw the intrinsic, it would be way down here. So we have a very nice channel. This is very much in strong inversion because the conduction band actually crosses the Fermi level. So we have a very nice channel, and we denote that by these little black balls here, which are electrons. They're sitting right at the surface. Another way to look at this is they're sitting in a notch. They're basically in a big well. You can think of this as a water well. Then they can't get out. So they're that's a good thing. They're stuck in this notch. Well, where did this notch come from? And that is what we're going to investigate right now. Notches are really, really good things to have. And so what I'm saying here is the oxide is not only an oxide, I'm going to call it, quote unquote, a semiconductor. We can look at insulators as being extremely wideband semiconductors. So this SiO2 layer, we can say, is a semiconductor which has a band gap of about 9 electron volts. It's huge, but it's still, we can look at it as a semiconductor. So I have two semiconductors. One is the oxide, the other is the silicon, one with a very high band gap, and the other with a very, well, not very low, but a much lower. This has a band gap of about 1.1, and 1.12 to be exact, electron volts, whereas the band gap here is 9 electron volts. So it's quite a difference, and we suspect that this notch formation has something to do with the fact that this has a wide band gap, the SiO2, and the silicon has a much smaller band gap. The other thing we suspect may be an issue is the affinities. The affinity is the amount of energy that it takes to take an electron from the conduction band, which is still inside of the semiconductor material, and to free it completely and to blow it off into free space. So E0 is the difference. E0 and EC is called affinity, and that's how much energy it takes to completely free an electron from the conduction band. And it's going to work out that the two issues that will determine the formation of the notch are the electron affinity differences. It's going to work out that the electron affinity of silicon is much greater than the electron affinity for SiO2, and the band gap differences. So those will be the two issues which are going to determine whether or not we get a notch. So notches are good. What's not so good? Well, the fact is that we have a very high doping here it's about 10 to the 17th or more, maybe 10 to the 18th, somewhere between 10 to the 17th and 10 to the 18th. So a notch is good. Doping is not so good because the higher the doping, the lower the mobility, and the current is directly proportional to the mobility. Remember, the coefficient had Cox in the numerator, W over L, and the mobility also in the numerator. I should say Cox was in the numerator, not the denominator. So Cox W over L times the mobility. That is the total value of the coefficient, which appears in all the calculations for IDS. So mobility low, not good. So people started thinking, wouldn't it be nice if we could create a notch, but have a surface which had a low doping, maybe an intrinsic doping. The doping, again, for silicon, or the MOS structure, let's say over 10 to the 17th, mobilities can be in the well under 100, because not only do we get scattering from the dopants, ionized dopants, but we also get surface effects. So mobility for a MOSFET can be 50, 60, 70. If we had an intrinsic, we've seen the mobility for intrinsic silicon can be, for electrons, can be 1,000. So if we could increase the doping by a factor of 10, that would really, really be a big deal. So that's what people started to think about that, and then that is what caused the birth of the high electron mobility transistor. So let's start our discussion and rules for drawing energy band diagrams. And there are how many rules? About 6 rules. Okay. Most of them are very straightforward. There's one that we're going to be talking about in a little bit more detail because it's not quite as obvious, and it's the most important one, and that is number 2. Number 1, in equilibrium, the Fermi level is horizontal over the entire structure, and that's always true because in equilibrium there is no mass transport. Mass transport would require the Fermi level have somewhere a discontinuity. So that is rule number 1, which we've seen through all of our devices, from the Schottky to the PN junction to the ISO junction to the pin to the, you name it. Every single structure has an equilibrium, has a Fermi level which is horizontal and flat. The second one is that the free electron curve, the E0 curve, be smooth and continuous, and we're not going to allow any discontinuities in E0. So when we make our more complicated devices, E0 is going to be nice and smooth and continuous, whereas E sub C and E sub V, we're going to allow at least quasi-discontinuities. We're going to allow jumps there, and we're going to have to explain why we do that. Okay, the energy difference between the conduction band and the free electron level is called affinity, and that is this difference right here between E sub C and E0. And that's one of the important parameters. The other is the work function. The difference between affinity and work function is that the affinity is a material property. It does not change with doping, whereas work function does change with doping. Remember, the work function is the difference between E sub F and E0. And as the doping goes up and down, the Fermi level goes up and down. So the work function is a function of the material and the doping, whereas the affinity, which this EC is fixed in space and E0 is fixed in space, so that the affinity is only a function of the material. Okay, and rule number 4, which is the kissing cousin of rule number 3, is that the conduction and valence band edges, these two guys, can have relatively steep quasi-discontinuities. They can have jumps up and down, and we're going to explain that in just about a minute. First, let's take a look at rule number 5. Away from the junctions, the band gaps do not change because the band gaps are material properties. So if we have two different semiconductor materials, we'll have two different band gaps. And the band gaps generally do not depend on the doping. There's a very slight variation. At high dopings, band gaps decrease, but very, very slightly. So to first order, we can say that the band gaps do not change with doping. And as always, the N band bend up and the P bands bend down. Okay, so finally, let's take a look at condition number 2 and compare it to, I guess, condition number 4. What we're saying here is the free electron level must be smooth and continuous, whereas the band edges, let's just take a look at E sub C, for example, does not have to be smooth and continuous. So if we go back here and we take a look at E sub C, this is, if we have a quasi-discontinuity or a jump, it means we're going to have a high electric field in the semiconductor. Now, if we take a look at silicon, going back to our velocity saturation, velocity saturates at about 10 to the 7th centimeters per second. The electric field associated with that velocity saturation is about 10 to the 4th volts per meter. That is an extremely large electric field, but we get no deleterious effects. The semiconductor doesn't, sparks don't come out of it, or all kinds of, it doesn't break apart or anything like that. In fact, we can get a lot higher than 10 to the 4th. We can go an order of magnitude higher, or perhaps even more, 10 to the 5th, 10 to the 6th, maybe even volts per centimeter. Huge electric fields because it is confined in the lattice of the semiconductor. Of course, if one goes into the nucleus, the fields become astronomical. Not so in free space. What's the highest electric field we can think of in free space? And that would be, say, lightning. And lightning has associated with some pretty high electric fields. I don't know what the actual, I try to look up what the magnitudes are. They're comparable, I believe, to about 10 to the 4th or 10 to the 5th volts per centimeter. But of course, lightning is something that we want to avoid at all costs. It is not a normal effect of an electron freeing itself from a semiconductor. So I can have large electric fields in the semiconductor, which means that implies that I can have jumps in E sub C, but I cannot have jumps in E0 because I cannot have free space simply does not support large electric fields, and that is a very critical condition for drawing energy band diagrams. Okay, so now let's get going and see how it goes. We're going to start with the homojunction. Just to review, this is from chapter 11, p-n junction. The Xi's are the same because silicon is silicon, same material, same electron affinities. But of course the work functions are different because the P Fermi level in the unattached material is closer to the valence band, and the Fermi level in the N-type material is closer to the conduction band. The N bands bend up, the P bands bend down as we approach the metallurgical junction. So that's a homojunction. And now let's go to the most general case where everything is different. Not everything. The two main things that are different are the band gaps. Here we have a higher band gap in, actually I don't know if it's higher or lower. We're going to say that EG1 and EG2 are not the same Of course, the band gap, again, the difference between the valence and the conduction bands and the electron affinities are not the same. So we have 4 parameters which are different, and these are material properties only. Okay, now we're going to apply this to 2 separate systems, and this may seem really kind of nitpicking and almost silly, but we'll see why in a little bit. First system is where the p-type is on the left and the n-type is on the right, and then we're going to reverse it, putting the p-type on the right and the n-type on the left. And the reason that this does make a difference is eventually we're going to put one of these levels on top and the other level on the bottom. So if I didn't differentiate between right and left, I'd have to differentiate between how I rotate. So we rotate one way, and then we have 2 different systems. So we'll go over these, some of them rapidly, until we get to the one that we really are interested in. Okay, again, we begin with the homojunction, equal band gaps, and equal affinities, and that's exactly what we had here. Xi1 is equal to Xi2. This is P on the left and on the right, and the band gaps are the same. Okay, now we get to the real deal. A completely idiotic, unrealistic case, but we'll just look at it anyway, where the band gap, we'll see why it's not realistic in just a little bit, where the band gap of semiconductor material 1 is greater than the band gap of semiconductor material 2. This distance here is less than this distance here. However, the affinities are the same. So if the affinities are the same, Xi2 and Xi1 are equal, then E0 precisely follows EC. However, if we start from the P side and we go and we jump right at the metallurgical junction, the band gap immediately goes down, which means I have this jump up right here. So this is the delta EG minus E1, and that is this distance from here to here. So we have a notch in the valence band. That's a rather interesting case. It is not a realistic case. Okay, and we'll see why in just a little bit. Now consider the case where EG1 is greater than EG2, band gap material in semiconductor 1 is greater band gap in semiconductor material 2, but the affinity in semiconductor 1 is less than the affinity in semiconductor 2, and it works out that this is a realistic case, except that the placements are not quite what we would like. Okay, so in that case, we keep this part of the diagram exactly the way it was here. However, when we get to the metallurgical junction, when we go from Xi1 to a lower, from a lower value of Xi1 to a higher value of Xi2, we get a jump down, and E0 does not follow E sub C. We actually get a jump in E sub C, but not in not E0. So that's the heterojunction where we have this condition. So one of the obvious conclusions here is we have a difference in electron affinities. We will have E0 not following E sub C. There'll be a difference in the free electron level versus the conduction band level because of the fact that the affinities are different. Okay, so now let's go to the second type, where we simply flip the positions. Here the P was on the left, N was on the right. Now we're going with N on the left and P on the right. And again, we'll start with the homojunction. Very simple case, exactly the case that we had when we reversed the two. all the bands follow, and nothing terribly exciting about that. Okay, next case, we follow exactly along as we did in system number 1. Now, again, the N is on the left, P is on the right. We have EG1 greater than EG2, but the affinities are the same. Again, unrealistic. We're not going to use it. We're just trying to put it in there more for fun and for clarity. So if the affinities are the same, then E sub C and E0 follow one another. Just a carbon copy. Same exact thing. And all the action is with the in the valence band. But look at the difference between the valence band in this condition where N is on the left and P is on the right, and compare that to the one here where we had exactly, no, that's not the one. Now here it is. Exactly the same thing. Here we had a notch in the valence band, and if we reverse the position of the N and the P, we have a jump in the valence band. So that's one of the reasons that we have these two different systems. And finally, we have the reaching the promised land. This is the real deal. And on the left, P on the right, the band gap of semiconductor 1 is greater than the band gap of semiconductor 2, but the affinity of 1 is less than the infinity of 2. There is an inverse relationship, and we're going to see, at least empirically, why that's true. The reason theoretically is in the text in chapter 9, but it's one of those sections that we did not cover in our sessions. So here we have a jump in the valence band, but the jump in the valence band could be essentially 0 if these differences are equal. If EG and delta EG and delta EC are close, then this jump will be very small. However, since Xi1 is less than Xi2, we have a notch in the conduction band at the metallurgical junction, and E0 is nice and smooth and continuous. Okay, so the main takeaway from all of this is the most important condition, and we will have a notch if we have two semiconductor materials. The left one has the smaller electron affinity, and the right one has the larger electron affinity. So that's the condition right here to form the notch. One more case, which is, again, not a normal case, where we have the same condition as here, but with this time with equal band gaps. Again, totally unrealistic, but we do it anyway. And if we have that condition, then we will have the notch because of the difference in the size. This is the red line here, would be the homojunction, where we have equal size. And if we have equal band gaps, EG1 equals EG2, then the valence band follows the conduction band, and we have notches in both the conduction band and the valence band, and those notches are the same. Again, that's not realistic, just for clarity. What the heck? Okay, now let's put all this good stuff together and ask some questions. And this is the big one. Is there a correlation between electron affinity and band gap? And the answer is a resounding YES. Absolutely. There's actually an inverse correlation. Can we predict electron affinities based on material composition? Maybe. Can we engineer electron affinities independent of band gap? That is Probably not. We can engineer band gaps, and once we have the band gaps, the electron affinities will be determined. And, okay, where do the charges come from to fill the gap? Well, we'll see a little bit. And 5, how do we control the channel conductivity? And that, again, is the whole purpose of the FETs. Okay, so before we answer the big question, number 1, let's go back and look at the relevant rows and columns for semiconductor materials that we'll be considering. We have been considering silicon germanium. We're going to be taking a look at silicon carbide a little bit. Of course, gallium arsenide. We'll be taking a look at aluminum, gallium arsenide, and we'll be taking a look at gallium nitride. All of those. And let us now, okay, before we go to that, the issue is that we saw way back in chapter 2, and it is a really big deal. As we move up in rows, we go to bigger, the smaller atoms. The smaller the atom, the more tightly bound the electrons, and the wider the band gap. That was the big conclusion of chapter 2, which means that carbon, crystalline carbon, also known as diamond, has a much larger band gap than silicon. In fact, I think it's about 5.5. Silicon is 1.12. Germanium is 0.67. Gallium arsenide, because it's a 3,5, has a larger band gap even than silicon, much larger than germanium. However, if we substitute aluminum for some of the gallium, we increase the band gap. So aluminum gallium arsenide has a larger band gap than just plain old vanilla gallium arsenide. And now we can take a look at these things right here. And of course, that is exactly what table 24.1 shows. Diamond, large band gap. Silicon, smaller. Germanium, smaller. Gallium arsenide, a little bit larger. Aluminum arsenic, much larger than gallium. I should say aluminum arsenide is much larger than gallium arsenide because aluminum is higher up, row 3 as compared to row 4. Aluminum nitride, bigger yet, because nitrogen is row 2 and arsenic is row 4. And gallium nitride, again, that follows because nitrogen has a larger band gap, or is higher up in the periodic table and arsenic, so that makes sense. And again, the aluminum gallium arsenide has a larger band gap than gallium arsenide. And the largest band gap of all is not even a semiconductor, but we can think of it as a semiconductor with band gap equal to 9. Now look at the Xi's. As we see here an interesting thing, that as the band gap gets larger and larger, the Xi's get smaller and smaller. So diamond with a very large band gap has a very small electron affinity. Silicon and gallium arsenide have about the same electron affinities, but aluminum arsenide, wider band gap, smaller electron affinity, and everything else follows very nicely. This is the big one right here. Aluminum gallium arsenide has a wide band gap and a smaller electron affinity than gallium arsenide. So this is the combination, gallium arsenide and aluminum gallium arsenide, that we'll be using. Large band gaps for the thing we're going to put on top, and smaller electron affinities, and that is what is going to form the notch. Okay, so let's take a look at that particular combination. So this basically is figure 24.9, way back here someplace, 24.9, same thing, okay? Except we put in lots more stuff in here, but it's the same picture. We have a wide band gap semiconductor on the left, a somewhat narrow band gap on the right, and the Xi the Xis are not shown here because we're not showing E0, but the Xi1 is less than Xi2 because the band gap is larger for semiconductor number 1. And the theory of all this, which we have written up in the text, it's called the Bardeen theory. We did not cover it in our sessions. However, you can read about it. It's in Chapter 9, Section 5. And we have the Bardeen theory tells us that there are relationships between conduction band minus E0 for the two semiconductors. These are the two Xis. They are related to band gaps by this thing called R. And for many semiconductors, specifically for silicon and gallium arsenide, R is on the order of 0.67. That's what the theory says, and there is a kind of a cheap proof in the text. And the Bardeen theory, this again comes from John Bardeen. We'll have a little bit more to say about him in the wrap-up. One of the really true great geniuses of the 20th century. Okay, so now we're going to look at a real high electron mobility transistor, and we are going to use the AlGaAs gallium arsenide system as one system, and then we'll talk about the gallium nitride, aluminum gallium nitride system as a second system. But the one we're going to look at, spend a little bit more time in, is the AlGaAs gas. AlGaAs again being aluminum gallium arsenide, and that will be our N-type semiconductor. Of course, N-type band's bent up. It'll be on the top, or in this case on the left side, the way we've been drawing it, and it's in intimate contact with a undoped or intrinsic semiconductor underneath. The N-type semiconductor, because it has a higher band gap, will have a lower electron affinity than the undoped material, which has the smaller band gap. Okay, and that's basically what we're saying here. The small electron affinity corresponds to the larger band gap. So we choose the N material as our wide band gap and low electron affinity semiconductor. And in order to fill the states, we require that the Fermi level be somewheres in the notch. And let's see how that works. So enter the Fermi level. And here we have actually, we've drawn the Fermi level in either 2411, 24.9, whatever one wants. It's all the same. We have a notch in the conduction band. And if we have the Fermi level, this of course is a extremely heavily doped N-type material with a wide band gap. This is essentially intrinsic. It may be slightly P-type, doesn't really matter, but all states above the Fermi level will be filled. So these states here will be filled. When we put these two guys together, we have a high Fermi level, we have a low Fermi level. The Fermi levels equilibrate because it's in equilibrium, and we have electron transferred from semiconductor material 1 into semiconductor material 2, and they basically swarm into the notch. So here's the notch. It is on, or in, I should say, at semiconductor number 2 with the intrinsic, and that's the key, the intrinsic doping, essentially undoped. So it's got high mobility, it's got a nice channel, and that is a really, really good situation. So all these 3 electrons and lots more jump into this what we call quantum well, and it's a quantum well because this distance here is incredibly small. This is on the order of, at most, a few tens of microns. So that's the HEMT. That's it. The only thing left to do is to confirm, or, well, we're going to check out the Bardeen theory and see if it makes any sense. And that is figure 2412b. So in 2412b, I have actually drawn the E0. I didn't want to clutter this up too much. It wasn't particularly relevant. The idea here is that electrons go from this highly doped N material into the intrinsic semiconductor material directly underneath of it in intimate contact. So now we draw E0, and I want to find out what this height of this notch is. Of course, the notch is going to be just psi2 minus psi1, or equal to delta EC. That's the difference between here and here. And, of course, delta EG is just EG1 minus EG2, and that's a positive number. And the Bardeen theory says that delta EC is equal to delta EG multiplied by R. And again, the R is somewhere around 0.6 to 0.7. So we put in the numbers for the gallium arsenide, aluminum gallium arsenide theory, the affinities for gallium arsenide 4.07, the affinity for aluminum gallium arsenide 3.6, and we asked, I should put a question mark here, is that equal to 0.67, which we're going to assume is R, multiplied by the difference in the band gaps, and indeed it is. So John Bardeen was right. He usually is right. You don't argue with Bardeen. There's a guy, the only human being to ever win 2 Nobel Prizes for physics. So when he says it's right, it's right. We can believe it. And here again, this is just basically 2412b redox. It shows the electrons swarming into this extremely narrow quantum high mobility channel. So the two main systems today, there are others, but these are the two big ones, the aluminum gallium arsenide on the left, gallium arsenide undoped on the right with X about 0.47. That's the one we've been discussing on all of these pictures. And the other one is the aluminum gallium nitride. And this should be gallium nitride, not gallium. I don't know what that A doing there is. Let's take that out. Naughty, naughty. Okay. With X, somewhere about 0.33. So if you look at this system, the aluminum gallium nitride, if we take a look at aluminum nitride versus gallium nitride, the aluminum nitride, because it is in, I believe, row 2, has a much larger band gap and a much smaller electron affinity than gallium nitride. We can vary the percentage of aluminum, where the percentage of aluminum is given here by X. So X goes from 0 to 1. If X equals 0, it's gallium nitride, band gap, affinity. If X equals 1, then it's aluminum nitride with the larger band gap and the lower electron affinity. So now if we look at the just a kind of a general case of the MOSFET versus MESFET versus HEMT. These are kind of general considerations. The channel formation, of course, in the MOSFET is through substrate inversion. In the MESFET, we have a channel deposition, which is very expensive. In the HEMT, we form a quantum well by putting two materials, a high band gap next to a lower band gap material. The channel charge in the MOSFET, it's due to the inversion in the MESFET, we dope the channel, the deposit layer is doped, and here the high band gap material is heavily doped. The gate in the MOSFET is generally polysilicon. We haven't been able to produce metal. In the MESFET, it is metal. It's a metal semiconductor, both in the MESFET and the HEMT, forming a Schottky barrier. The charge control the channel is controlled by the gate voltage, which we have seen many times in the MOSFET. In the MESFET and the HEMTs, we pinch off the channel again by controlling the Schottky barrier. Okay, so let's just say just a couple of words about the HEMT, the high electron mobility design. And this again is covered in much more detail in a wide bandgap semiconductor course. Here we have the gate metal, generally, I believe it's gold. I'm pretty sure it is. It's been a while since I dealt with HEMTs in the lab, but I believe it's gold. And then underneath, we have the wide bandgap material, the AlGaAs. So we have a metal semiconductor junction here at this interface, and then we have the intrinsic, the low doped or intrinsic gallium arsenide narrow bandgap semiconductor. So here we have a semiconductor. So we have depletion regions at the Schottky barrier. That's this guy right here, this red line which curves up. And then we also have depletion regions at the semiconductor, because this is like a PN junction. So we have two depletion regions, one shown in red and one shown in purple, and they're labeled depletion region 1 and depletion region 2. And underneath the whole shoot and match, we have a semi-insulating gallium arsenide, just like we had in the MESFET. I should mention one more thing. I probably should have mentioned it back here. And the AlGaAs, we cannot, or we are not able to grow gallium nitride pools. So we generally deposit layers, first of gallium nitride and then of aluminum gallium nitride, one on top of the other. And the substrate is semi-insulating silicon carbide. And I believe sapphire is also used. So that's just a point of clarification there. So if this was a GaN system, this would not be semi-insulated gallium arsenide. It would be semi-insulating silicon carbide, which is also reasonably expensive, and we certainly don't get it in 12-inch or 15-inch wafers. I think we may be up to 4-inch wafers these days. So now I'd like to take a look at this region right here, because there is one component which is missing, and we want to find out. Actually, there's two design considerations which we'll very briefly discuss, and there's a missing layer here. I'm trying to give a reason why we need another layer between the yellow and the orange. First, let's take a look at this region right here, and we've blown that up. We have this depletion region, which is depletion region number 1. That's this guy, and then we have depletion region number 2 underneath, and that is this one right here. And then we have the channel formation, which is in the gallium arsenide intrinsic. And the deal is here, we would like these two depletion regions to merge. We don't want a high conductive layer in this yellow region right here. And the reason is because we're putting a source over here and a drain over here. And if we have a low resistance region right between the purple and the red, we're going to get lots of current, and that ain't good. because it may be low resistivity, but it is also very low mobility. And so we'd like these two regions to merge. In other words, we want the yellow region to be completely depleted. And in order to do that, we want T1 and T2 to add up to T. And if we do the relatively simple calculations, we have degenerate doping of about 10 to the 19th. We find that the depletion region is about 100 angstroms, and that is going to be the same for both T1 and T2, because the depletion region is always on the lightly doped side. So the depletion region is always on the lightly doped side of the p-n junction. The depletion region, if it's a metal semiconductor, of course, is on the semiconductor side. So this would be the depletion region for a Schottky barrier doped to 10 to the 19th, and it's about 100 angstroms, and that is about the same as the depletion region on the quote-unquote lightly, or I should say the heavily doped side of this p-n junction. We don't care about the depletion region so much here. We do care about the depletion region here. So we're talking a distance here of about 200 angstroms. So we need to be sure that the deposition is on the order of that total depletion width. So 250 angstroms, very, very small, a very thin deposition region indeed. And now there's one more consideration. And if you take a course in wideband semiconductors, they give all kinds of the graphs and pictures and maybe even some calculations. But the idea here is that we have a depletion region here. And if we have a depletion region in N-type gallium algas, we're going to have lots of positive fixed ions. So we have lots of positive charges right up here, and those charges produce electric field lines, which will end in the channel. So that's not good, because that is they're going to be centers for scattering and lowering the mobility. So what we do is, between the yellow and the orange, we put what we call a spacer level of undoped or intrinsic gallium arsenide to kind of suck up some of those positive charges. So actually we have three layers. We have under the gate, we have the degenerately doped algas, we have a thin spacer layer, and then the undoped gallium arsenide. So that's a very puny reason why we put in this spacer level. Okay, so again, finally, we summarize the MOSFET and the HEMT as far as their energy band diagrams. High band gap, low electron affinity, higher electron affinity, notch. Same thing. And that is what got to people to thinking about, this is the normal kind of plain vanilla MOSFET. Why can't we do something which has the advantages of the MOSFET, but has higher mobility, and mobilities in HEMTs can be well over 1 million as compared to mobilities in MOSFETs that are on the range of, we're lucky, about 100 or so. So a huge advantage. And if we go at lower temperatures, we can get mobilities in the many millions for the HEMT. So that's it for the high electron mobility transistor. And in our next and final session, we'll be talking about comparing the MOSFET with the MESFET, and we'll be looking at the IV characteristics of the MESFET, which we did not consider in chapter 20. And we're going to end with the finale of the wonderful movie called Soul Keeper, the story of Sabrina Sperling and Carl Jung. And it ends with the song Tumbalaika, which is quite a beautiful song. A young boy is talking to a maiden, and he says, "Maiden, maiden, tell me true, what can grow without dew? What can burn for years and years? What can cry and shed no tears?" And the maiden responds, "Barishable, silly boy, a stone can grow without dew. Love can burn for years and years. A heart can cry and shed no tears." And we'll see you next time.
Вы не можете это делать! Вы не можете делать это! Это же храм Божий!
Befiehl deinen Leuten, sich hinzuknien!
Пожалейте! Пожалейте хотя бы детей и женщин!
Встать на колени!
Встаньте на колени!
My name was Sabina Spielrein. When I am dead, I want Dr. Jung to have my head. Only he is to open and dissect it. I want my body to be cremated and the ashes to be scattered beneath an oak tree on which is written, I too was a human being.
Steht a bocher bonner Tracht und Tracht a ganze Nacht. Nehmen zu nehmen, nur nicht verschämen, nehmen zu nehmen, nicht zu verschämen. Tumala, tumala, tumala like, tumala, tumala, tumala like, tumala like, spiel balalaike, spiel balalaike, freilich soll sein. Mädel, Mädel, ich will befregen. A Stein kann wachsen an Regen. Liebe kann brennen und nicht auf Herren. A Herz kann denken, weinen und rennen.